Welcome. I am so thrilled you're joining us today because, well, we are going to unpack something absolutely fascinating. We're taking a deep dive into a comprehensive review from the journal Progress in Materials Science, and it's a wild ride. We're going to explore how an incredibly common, clear rubber is literally being transformed into a high-tech superpower right before our eyes. So let's just jump right in, shall we?
I want you to think about the technology you're using right now. Chances are it's made of rigid plastics, glass, stiff silicon chips. But what if I told you that the actual fabric of tomorrow's technology isn't hard or brittle at all? If our devices are going to seamlessly integrate with our bodies and our environments, we have to rethink the very materials we use. We really need them to be soft, stretchable, and dynamic. And this is exactly what I mean. Imagine flexible, glowing circuits that can be bent and rolled up without snapping or breaking. I know it looks like science fiction, but this is the actual end goal of modern material science. We're moving towards seamless active materials that can withstand all the physical stresses of the real world, all while conducting electricity or emitting light. And the secret ingredient making this whole shebang possible? It's a material known as a PDMS composite. To really understand how we get to those glowing, bendable circuits, here is our roadmap for today. First, we'll meet our supermaterial, then a brief history of PDMS, the nanoparticle upgrade, how they're made, tech applications and superpowers, and finally, we'll look at the future of soft tech. All right, section 1. Meet the supermaterial, the blank canvas. Before we can talk about glowing circuits and high-tech sensors, we have to introduce our foundational hero. It's polydimethylsiloxane, or thankfully PDMS for short. Think of pure PDMS as the ultimate, highly capable blank canvas for scientists. If you look at its molecular backbone, you'll see the central chain made of alternating silicon and oxygen atoms. Now, those specific silicon-oxygen bonds are absolutely crucial. They require a ton of energy to break, which makes the material incredibly stable. While those methyl groups hanging off the sides, they give it its unique physical properties. And those physical properties are quite literally natural superpowers. Pure PDMS has a light transmittance of over 90%, meaning it's almost perfectly transparent. It has high hydrophobicity, basically it repels water beautifully with a contact angle up to 110 degrees. It's extremely flexible, completely biocompatible, and even acoustically tunable. But here's the catch. While pure PDMS is a fantastic water-repelling base, on its own, it's totally passive. It just acts as an insulator. So to become truly active, it needs an upgrade. But before we upgrade it, I really want to highlight this number, 300 degrees Celsius. That is how thermally stable this blank canvas is. It literally doesn't break down until it hits roughly 300 degrees. And on the flip side, it remains flexible all the way down to a freezing glass transition temperature of negative 120 degrees Celsius. I mean, that extreme durability is exactly why scientists chose it as the ultimate foundation to build upon. Moving on to section 2, a brief history of PDMS, from lab to microfluidics. Grounding this material in reality shows us just how rapidly it's evolved over the decades. Pure PDMS was first synthesized way back in 1940 by GE and Dow Corning. By 1955, we saw the first silica composites used to reinforce the rubber. But the real explosion in high-tech applications, that kicked off around 1990 with the very first PDMS microfluidic devices. And, jumping to the 2020s, we're now creating advanced nanosponges in complex wearables. It took decades to go from basic synthesis to this cutting-edge stuff. And that major leap forward was all thanks to what we're going to look at next. Section 3. The nanoparticle upgrade, adding the magic dust. Okay, so this is the core concept of today's explainer. We take our resilient vanilla PDMS hero and we add what I like to call magic dust, specifically engineered nanoparticles, to unlock entirely new abilities. These nanoparticles act like specialized sidekicks. Think of each type as a different kind of paint on our blank canvas. Add gold nanoparticles and suddenly your rubber has stretchable conductivity. Add silver and it becomes antibacterial and can actually sense pressure. Mix in zinc oxide, and the rubber generates up to 4.2 volts of piezoelectric energy just by being compressed. No way, right? Silicon dioxide boosts mechanical strength, and copper oxide creates anti-corrosive temporary bone implants. It is just beautifully modular. But you can't just dump this magic dust in randomly. You have to achieve what scientists call the electrical percolation threshold. Basically, this is the exact moment the nanoparticles connect with one another inside the rubber matrix to form a stable, continuous pathway. For example, in silver-infused PDMS foams, hitting the precise percolation threshold allows the network to sense micropressures as incredibly low as 25 pascals. It's literally like flipping a microscopic switch.
However, getting that perfect network is tough. On one hand, you can have good even dispersion, but on the other hand, you can get agglomeration. If scientists add too many nanoparticles, usually above 8 to 10% for some materials, the particles clump together into these big voids and clusters. When they clump, the material loses its flexibility, gets brittle, and, well, totally ruins the whole point of using rubber in the first place. Which brings us to Section 4, how they are made, mixing versus synthesizing.
So how do we get the magic dust into the rubber without causing those terrible clumps? Well, the traditional method is called ex situ mixing, and it's essentially like baking a cake. You start with liquid, uncured PDMS prepolymer, you physically mix in your pre-made nanoparticles, maybe using some solvents or a mechanical stirrer, then you put it in a vacuum chamber to degas it, pulling out all those trapped air bubbles. Finally, you apply heat to cure it into a solid state. It's easy and it's great for testing new recipes, but like I mentioned, physically stirring them often leads to those pesky agglomeration clumps.
Now contrast that traditional mixing method with some brilliant advanced methods called in situ synthesis. Instead of mixing pre-made dust into the rubber, scientists put the chemical precursors right into the liquid rubber and actually grow the nanoparticles directly inside the PDMS matrix. As the polymer cures, the particles simultaneously form and lock into place, giving you a perfectly uniform distribution without any of the clumps.
One of the most powerful in situ methods highlighted in the research is sol gel chemistry. By using precursor chemicals like TIOS, scientists can perfectly tune the size and shape of the silicon network growing inside the PDMS just by using an acidic or basic catalyst. Acidic environments yield smaller, homogeneous domains, while basic environments promote controlled aggregation. This seamless growth organically enhances the material's resistance to chemical degradation, extending its lifespan far, far beyond standard rubber.
All right, Section 5, Tech Applications and Superpowers. We've talked a lot about the microscopic chemistry and the manufacturing, but why does this actually matter to you? Let's connect all this science to the macroscopic, everyday applications that are changing the world right now. Because PDMS is highly biocompatible and can be molded at the microscopic level, scientists are creating organ-on-a-chip devices. They can literally make a microchip that mimics the exact mechanical strains of a human gut epithelium. Or they can build an ultra-fast spiral microchannel that takes a raw blood sample and physically separates the red blood cells from the plasma in seconds. It's wild. And the list of cutting-edge applications just goes on. We're talking about flexible strain sensors that monitor human motion for exoskeletons, wearables that harvest kinetic energy using zinc oxide, super soft adhesives that securely attach to wet biological tissues without damaging them. We're even seeing temporary antibacterial bone implants using copper oxide that heal the body, and advanced membranes that can physically separate CO2 from nitrogen gas to help fight climate change. I mean, none of this is possible with rigid old-school silicon chips. And our final section, the future of soft tech. The research makes it super clear that we're in the middle of a massive paradigm shift in material science. The stark contrast between the past and the future really says it all. The technology of the past relied on rigid, brittle, single-use plastics and stagnant interfaces. But by harnessing dynamic covalent chemistries and self-assembling nanoparticles in PDMS, the future is looking incredibly bright. We're looking at a future filled with recyclable, self-healing, dynamic, and adaptive soft composites. Just imagine a wearable device that gets scratched and simply heals itself at room temperature, because the chemical bonds inherently want to reconnect. So, I want to leave you with this provocative thought. If our technology can now bend without breaking, if it can heal itself dynamically and adapt to its environment just like biological skin, what limits are left to break? As materials like PDMS nanoparticle composites continue to blur the line between biology and machinery, the next decade of soft robotics and flexible electronics is going to be absolutely spectacular. Thank you so much for exploring this fascinating materials science review with me on this explainer. Keep your eyes on this space because, for sure, the future is definitely flexible.